Hello, everybody. In this video, I thought, let's just go ahead and tackle something rather profound. Let's talk about the elements on the periodic table and where they come from. Where do we get the calcium in our teeth, the iron in our blood, the carbon that makes us up? Where do we get the oxygen that is part of water, H2O? Have the elements on the periodic table always existed since the start of the universe? No. Other than hydrogen, helium, and just a smattering of lithium, all the elements on the periodic table have been created after the Big Bang. A lot of them have been forged in the nuclear furnaces in the cores of the stars that we've talked about during their stellar evolutionary cycles as they evolve towards death. They're fusing lighter elements into heavier elements. And that's just one of the several processes in which we can build out all of the elements on the periodic table. This process of generating the elements, of synthesizing the elements, is the scientific field called nucleosynthesis. That's the topic of this video and the topic of the next video. Let's go ahead and get to it. So, we have that big question of where do all the elements on the periodic table come from? We're going to talk about nucleosynthesis, which is the generation of the elements of the periodic table. But I really like how Carl Sagan sort of framed this and gave this a little bit of context. He had a natural ability to make these complex ideas both simple and profound. So his take on nucleosynthesis, although I'm just picking one quote out of an entire series of things that he said on the topic, well, I'll do my best. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. And this is literally true, other than all the hydrogen and a good amount of the helium. All of the stuff is related, all the other elements are somehow related to the birth, life, and death of stars. The stars are our creators of the elements on the periodic table. The stars are what create the atoms heavier than helium. So if we are going to understand this, we need to understand the evolution of low mass and high mass stars, which we've done. We spent a long time doing that, and those fusion reactions that were occurring in the core. This has armed us, this has equipped us to now tackle this profound topic of nucleosynthesis, the creation of the elements. And nucleosynthesis literally means the synthesis of atomic nucleo or atomic nuclei. Nucleo, relating to the nucleus of atoms, synthesis, synthesizing, generating, creating. So nucleosynthesis literally is the synthesis of atomic nuclei, the creation of all of the elements on the periodic table. And we have a variety of ways in which we can create the elements on the periodic table. This is one of my favorite versions of the periodic table. I encourage all of you to get your own version of this. You can either rip it off out of my lecture slides or you can search for it on the internet. But this is a periodic table that shows the nucleosynthetic source of the elements on the periodic table. So instead of dividing them into their different groups like the alkalis, the alkali earths, and things like that, and the noble gases, what it does is it's coloring each one of the elements by how that element is produced. What nucleosynthesis produces that element. And it breaks it down into a variety of things. We have Big Bang. So the initial moments of the Big Bang when the universe was incredibly small and incredibly hot, or I should say the universe was crammed very, very, very close together to a high density and a very high temperature. As it expanded and cooled, our first element started to form via a fusion process, and that created hydrogen and helium, and just a smattering of lithium. So we have Big Bang nucleosynthesis. Then we have the dying of low mass stars as they go through their asymptotic giant branch, planetary nebula, and end up as a white dwarf. We get a lot of creation of the elements on the periodic table during the asymptotic giant branch via a neutron capture nucleosynthesis. Don't worry, we'll get there in the next video. We have the explosion of massive stars. We have supernovae explosions that create a smattering of elements. They're colored in yellow, and you can see which ones they prefer to create. And you can see now that there's a little bit of overlap. Some elements are created by multiple processes. Sometimes they're of the same isotope of that element, sometimes they're different isotopes of that same element. And then we have the merging of neutron stars, a emerging idea that's sort of been changing and replacing all of the yellow, the supernova explosions, by the merging of neutron stars appears to be one of the main drivers of the heaviest elements on the periodic table. And then we have the other exciting explosions, our carbon detonation, our type 1a supernovae explosions, which produce their own suite that are colored sort of in the gray tones right here. And then one that we won't talk a whole lot about is pretty much only responsible for creating beryllium and boron cosmic ray fission. Not a topic, it's kind of a niche topic, nothing I'm going to cover in this class. And of course, humans, we can synthesize some of the elements. So we have human synthesis of the elements, ones that don't occur in nature. All right, so there it is. We're done. We created all the, okay, you probably want some of the details, especially since we've gained all of this knowledge so we can actually understand the details. And you might see as you go through my notes, I often replace the Big Bang with the everywhere stretch. This is me paying tribute to one of my favorite online videos about the Big Bang topic. It's created by Minute Physics, and they say that Big Bang is a terrible name. I 100% agree. That is an awful name. In fact, it was used as a derisive name to try to call the entire idea uh, like stupid on its face. And then it just became part of the popular vernacular. But in this Minute Physics video, which I will link in the README, they offer a better name for the Big Bang, the everywhere stretch. And that does warrant maybe just a little bit of explanation because the Big Bang was not big. It was at the time when the universe was actually incredibly small, crammed into a very, very, very small volume. Nothing big about that, but it was occurring everywhere. So it happened everywhere in the universe simultaneously. So it wasn't a big thing, it was an everywhere thing. And it wasn't a bang, it wasn't an explosion of any kind. What it was a rapid inflation and stretching of space. Space was creating more space as space expands out and stretches. It's a strange topic. I really encourage you to watch the video. And I wish I had some time to go into some of that. We'll talk a little bit about space time. And we began this semester by talking a little bit about how we can bend space and stretch space, well, expand space. So the Big Bang wasn't big, it was everywhere. And it wasn't a bang, it was a stretch, hence the everywhere stretch. All right, so here is our goal. We can actually look out into the universe using things like spectroscopy and start measuring the elements and start building up what their ratios are. How much hydrogen is there compared to how much oxygen? How much oxygen is there compared to calcium? How much iron compared to strontium? So on and so forth, where we can build up basically a catalog of how much of each element there is. And we probably want to pick some sort of a standard, like compare everything to how much hydrogen there is or how much iron there is. And the point remains that we can measure how much of each element there is out there in the universe relative to the other elements. We call this the cosmic abundances. How much hydrogen is there? How much helium is there? We can both observe this and we can model this, and we're trying to get the two to merge, because if we can model fully and reproduce what we observe, then we have a really, really awesome physical model for the nucleosynthesis of the elements. And this is our plot of the cosmic abundances. So here we have mass number. So the mass number not going to be the element number, but how many nuclear particles are there. And then we have our abundance relative to silicon. So silicon is our standard right there. But you can see hydrogen is the highest. So hydrogen is the most abundant element in the universe. Second most abundant is helium, so on and so forth. And you can see that we're really lacking these lithium, beryllium, and boron. Then we have these sort of evenly spaced peaks through here, where we have even peaks between carbon, oxygen, neon, silicon, sulfur, calcium. We have this, what we call the iron peak, where it peaks at iron, almost as if things are building up towards iron via fusion. And then things will fission down towards iron. So we're pushing the creation of iron by fission this direction or fusion this direction and fission that direction. And then you can see that there are some other subpeaks as well. So this is our cosmic abundances. This is what we're trying to understand. We need to create all of these elements in these relative proportions if we're going to understand nucleosynthesis. And I just want to go ahead and give you our ranked list of most abundant elements in the universe. I've done this by mass. I prefer by number, but I didn't go through the calculation to translate by mass to by number. But the most abundant element in the universe is hydrogen. No surprises there. Second most abundant, helium, then oxygen, carbon. So carbon and oxygen, where are those being made? That is our endpoint of fusion in our low mass stars, creating carbon and oxygen. Huh, interesting. So we have a lot of carbon and oxygen. And then our number 5 is neon, and then iron. No surprise that iron was going to make the list. And then magnesium and sulfur. So here's a interesting thing. Notice that I've put the element number over here, and other than element number 1, every one of these is even, almost as if there is some natural process that is driving a preferential creation of even numbered elements over odd numbered elements, an even number of protons. Strange. We can understand that, and we'll see that, and it's largely created by a fusion process, a preferred low or easy to do fusion process. All right, so now that we've seen what our goal is, let's go ahead and take a look at the major types of nucleosynthesis, the 3 that we'll talk about in this class. We have the Big Bang nucleosynthesis, which I've already mostly mentioned, and that's at the start of the universe during our everywhere stretch. As the universe expanded and cooled, we could finally start forming protons and electrons, and then the protons got together with our electrons, and we had hydrogen. And we could even drive hydrogen up to helium fusion in the earliest times before the universe expanded and cooled to the point where you couldn't create any more helium. So the universe was expanding and cooling, and the timescales for creating hydrogen to helium made it so that the universe expanded and cooled before you could really fuse anything past helium. You got a small smattering of lithium in there, but pretty much Big Bang nucleosynthesis, the Big Bang itself, created hydrogen and helium. And my mind gets blown every time I think about this, because if you think about, we are in large parts made out of water. There is a whole bunch of water, and a lot of the other things that we're made out of are molecules that have hydrogen on them. Every hydrogen atom that makes up the H2 part of H2O, and all the other molecules, all the hydrogen in the universe has been around since the Big Bang. So carried within us, or within this water right here, are parts of the Big Bang. So I'm going to drink a little bit of the Big Bang here. Tastes cosmically good. All right, so Big Bang nucleosynthesis creates our hydrogen and helium. Then we have stellar fusion nucleosynthesis, which we've actually covered a lot of the ground. I'm just going to add a couple of details that'll explain the proliferation of even numbered of elements. And as we saw, we have fusion in the cores of low mass and high mass stars. Low mass stars build up to carbon and oxygen. High mass stars build all the way up to iron. And then in the next video, we're going to spend our time talking about another type of nucleosynthesis, neutron capture nucleosynthesis, where a atomic nuclei will capture a neutron, add it to its nucleus, which will then radioactively decay, make an unstable isotope that will cause the atom to decay to a different element. There are there's more than 2 ways of doing this, but the 2 most common ways are called the S process for slow and the R process for rapid. And this allows us to build elements past iron. All right, so let's look at our nucleosynthesis by fusion. So in the cores of low mass stars, getting hung up on that typo right there, let's not worry about it. So stars less than 8 solar masses, we can generate iron or elements up to carbon, and we'll mix in some oxygen there as well. Which it's these low mass stars, and specifically what's going to be happening during the asymptotic giant branch, where we have to bring in some of this neutron capture stuff. But these low mass stars are pretty much responsible for all of the carbon rich dust in the universe. Carbon rich dust. That sounds like a great place to drive organic chemistry, to start building organic molecules, the basis for all of life. So there's the start of us. There's no us without fusion in low mass stars. So this dust is, where do we create this carbon-rich dust? It's created in the cooling atmospheric shells of, as those shells of the asymptotic giant branch are expanding outward, the temperatures get cold enough where you can actually start forming some molecules and some dust particles. So you will actually get the creation of this dust in the outer parts of the envelope, and then the expanding and escaping shells from asymptotic giant branch stars. And then in our high mass stars, so stars that have 8 times the mass of the sun or greater, stars that will have fusion happen in their core all the way up to iron. And it's in these high mass stars that we're going to preferentially create what are called the alpha elements via a helium capture process, where basically we're going to have a nucleus and we're just going to fuse a helium atom onto it. We saw the start of this whenever we took 3 helium nuclei and fused them together to form carbon in our triple alpha process. And then we got some of that oxygen by taking carbon and just fusing another helium onto that to bump it from carbon to oxygen. We're going to play that game out here in the high mass stars, where the temperatures and the conditions are good to set off what we call the alpha process and create the so-called alpha elements. So let's go ahead and take a look at the alpha process. This is happening in the cores of high mass stars, and that's a key part because that's where we're going to get the temperatures to drive the core up past the fusion ignition temperatures for higher levels of fusion, so we can fuse things all the way up to iron. But also, an important ingredient in this is that these cores of high mass stars will eventually reach incredibly high temperatures of about 3 billion Kelvin or so. And once you hit about 3 billion Kelvin in any part of the core, as gravity and more mass is being crunched on top of it, driving those temperatures up. But once you hit about 3 billion Kelvin, you could go ahead and look at the black body radiation. Your peak is now in gamma rays, where you're creating gamma ray photons that have enough energy to break apart atoms themselves. We discussed this in a very intense situation in core collapse supernovae, which is a very, very rapid process with very, very, very high energy gamma rays. These are lower energy gamma rays, but we're still going to be using them to split apart relatively weak atomic nuclei. Remember, when we use a gamma ray, when we use light, a photon, to disintegrate, to destroy, break apart a atomic nucleus, that process is called photodisintegration, disintegration by a photon. And this is going to be happening in the cores of these stars. Why is it important? Well, this photodisintegration is going to create an abundance, a large number of helium nuclei, also called alpha particles, and neutrons. Both of these are going to be key ingredients for driving nucleosynthesis, helium nuclei and neutrons. Because with all the helium nuclei that are being produced via photodisintegration, we now have a large amount of helium readily available everywhere in the core, where it can be fused onto heavier elements via a process, a generalized process called a helium capture. Take a element like calcium and fuse the helium nucleus onto it. Take an element like sulfur and fuse the helium nucleus with it. Each one of those would be called a helium capture. Our neutrons, we'll save that for the next video. They have a very important role to play in the neutron capture nucleosynthesis processes. But for now, let's put those on hold and focus on all these freely available alpha particles, these helium nuclei created by photodisintegration, because this is going to drive what's called the alpha process. And all the alpha process is we're going to build up elements by having an element that's already there, say silicon 28. So that'd be the number of protons plus neutrons. And we're going to fuse helium-4, 2 protons plus 2 neutrons, 4 nuclear particles. So we have helium-4. We fuse those together. So we do a helium capture. We fuse an alpha particle with our silicon, which bumps us up to sulfur 32. So we added 2 protons and 2 neutrons. We bumped up 4 nuclear particles. Repeat the process, so fuse the helium nucleus to our sulfur, and now we're generating argon as well. And remember, photodisintegration is happening, so we are going to have plenty of these base things of silicon and sulfur running around. But now we can fuse another helium onto our argon to create calcium. And notice we go 28, 32, plus 4 is 36, plus 4 is 40, plus 4 is 44, titanium 44, and the next one, chromium 48, iron 52, and then all the way up to nickel 56. And there we have our entire alpha process. Notice that all we did is we're just fusing one more helium nucleus, one more alpha particle, and we're getting all of these elements being created. So this alpha process is responsible for creating elements heavier than carbon and oxygen. And it's always going to create elements with mass numbers, total number of nuclear particles, number of protons plus neutrons, of 12, starting with carbon, 6 protons, 6 neutrons. And then we're going to add 4 more to it. 2 protons, 2 neutrons from our helium. So all of these have mass numbers of 12 plus 4 times however many helium nuclei you added onto it, which I've just called N right there. And this will go all the way up to nickel 56, which is radioactive and will decay to iron. So this is where we're going to create our iron. What are our elements that we are creating? Oxygen, neon, magnesium, silicon, sulfur, argon, calcium, titanium, chromium, iron, and nickel. Plus 4, plus 4, plus 4, plus 4, plus 4, plus 4. Nice even numbers right here. You do not have to memorize these, but I'm just going into it to really hammer in that these are all even numbers and to really hammer in the process. And with all those free helium nuclei created by photodisintegration, the cores of these high mass stars are just perfect environments to drive this alpha process. So now let's go ahead and take a look at this with the cosmic abundances up to iron. So we have our alpha process that's responsible for creating all of these, what we call alpha elements. These ones where we have created them via the alpha process. We start with carbon and then we add 1 to go from 12 to 16. So 12 plus 4. And then 20, 30, 40. And this is going to create the alpha elements, which are carbon all the way up to calcium. So here are alpha elements right here. And notice that they're nice and evenly spaced. And each time we're adding 2 protons. So we are going up element number 2. Carbon is element number 6. Oxygen is element number 8. So on and so forth. So we are preferentially forming all of these even numbered elements. However, notice I didn't include our titanium, chromium, and iron and nickel because these isotopes, titanium 44, chromium 48, iron 52, and nickel 56, are radioactive. These isotopes don't like having a nuclear makeup that balance of protons and neutrons, so they are going to try to change their nuclear makeup. They're going to change the balance of protons and neutrons in their core via a number of processes. They can spit out a alpha particle in a radioactive decay, or they can convert a proton to a neutron by spitting out an electron, and a few other things as well. But those radioactive decays will happen that'll turn unstable nuclei into stable nuclei. This is why you don't want to go into a room and start handling uranium, because uranium is radioactive. It is decaying, it is changing from one isotope of uranium into an isotope of another element. And in that process, it's giving off lots of dangerous particle radiation that will end up with you being dead. In stars, though, not so bad. You're not going to kill a star this way. So these titanium, chromium, iron, and nickel aren't included in the uh, alpha elements because they will radioactive decay into different elements. And that means that we're going to have a dearth. We're not going to have very many of these elements cosmically because the process is building them, builds radioactive forms of them, so they go away, they turn into something else. And notice that after calcium, we have this big dip. But then everything's driving things towards iron, so we have this iron peak. Where is that iron peak coming from? Well, iron 52 is radioactive. It's going to decay into something else. But nickel 56, which is radioactive, will decay by spitting out an electron, converting one of the protons to a neutron in nickel, creating iron 56. Same number of total nuclear particles, 56 of them. And this is where we're getting our iron. This is giving us our iron ash core in the core of our high mass star. So we have everything as we have the generation of iron, and then we're going to also be making iron because as we fission things, things are going to, on this end, will drive them towards iron. To go past iron, to build the elements over this way, past the iron peak, we're going to have another non-fusion related nucleosynthesis process. That is going to be the topic for our next video. Welcome to creating all of the elements in the universe. I absolutely love this topic. I look forward to seeing you in the next video where we build elements heavier than iron. I will see you there.